Okay, so this is a short one, just 3 examples. So now we're going to graph systems of inequalities in a coordinate plane. So recall that a system is 2 or more equations. Okay, so we're graphing inequalities. So we have to consider our shaded region. Whoop, this is going to be crazy. I'm going to start. Shaded region. It's a system, so when we find the solution to a system, we're looking for the overlap because we need both conditions to be true. All right, so my first one, I'm going to graph that like my line, y-intercept of -5, slope of 2/3, 1, 2, 3, down to left 3. Okay, it's a solid boundary line because it's greater than or equal to. Now, I like to graph both of them and then I do the shading, but we can look at them individually. Okay, so here's my line. I'm going to test the origin because I know 0, 0 is not on the graph. Is 0 bigger than or equal to -5? That is a true statement. So I'm going to highlight above my line. Okay, because that's the region that makes this inequality true. Now when I graph my quadratic, it's a downward facing parabola. A is equal to -1. It has a vertex of 1, and it has y-intercepts of 1 and -1. It is dotted because it's not equal to. So there's my parabola. Now, another difference between inequalities and a system of equations when they're equal to each other, equalities have 1, 2, or 0 points of intersection. So we're looking for where these regions overlap each other. So when I look at my quadratic, I'm going to again test the origin, 0, 0. Is 0 smaller than 1? That's a true statement. All right, so let me get my different colored highlighter. So now for my quadratic, I'm going to shade in between inside that parabola. So now the solution to this is the overlap of those 2 highlighted regions. So the solution, all the ordered pairs inside the parabola but above the line, would make that system of inequalities true. So now here, you don't have to write an interval. It's all about the overlap of the shaded region. Okay, so y is bigger than -x and y is less than the quadratic. So -x, that's a line with a y-intercept of 0 and a negative slope. Okay, my boundary line is dotted or dashed. It cannot equal it. No. Okay. Zoomed it in there for you. So now here, 0, 0 is on the graph of the boundary. So I'm going to plug in the point 1, 0. So is 0 bigger than -1? That's a true statement. Okay, so here's 1, 0. That's what I use as my test value. So I'm going to shade this region, okay, above the line there. All right, so now when I graph my quadratic, so my quadratic is a horizontal shift. It's x squared, but I'm moving it to the left 2 units. So now my vertex goes from 0, 0 to -2, 0. Okay, -2 is my bounce point, so bringing back what we know about that exponent of 2. And then your y-intercept, if I make x equal to 0, 2 squared would give me 4, so my y-intercept is 4 if I want to get another point on the graph. Using my line of symmetry, I'm going to have that point on the graph of the parabola. It has to be a solid, or excuse me, a dashed boundary. So, creating my parabola. All right. Oh my gosh. Into my quadratic, I can also test the origin. So if I test 0, 0, because 0, 0 is not on the graph of the quadratic, is 0 smaller than 4? That's a true statement. So now I'll use my highlighter. 0, 0 is the true region. So I have to shade outside of my quadratic. This is what makes that statement true. Okay, so now when I go to answer the solution to the system, the overlap occurs here, outside of the quadratic, but above the line. Okay, so here's one. It also occurs here. Okay, if I were to extend my parabola, outside my parabola, but above that line, y is equal to negative x. When you do these, we will provide graphs for you so that you can graph them as accurately as possible. Okay, last example. X is less than or equal to the absolute value of 2. All right, I'm going to change this one to be the absolute value of x is less than or equal to 2. So let's change that first function to be the absolute value of x is less than or equal to 2. Okay, so now when we have absolute value inequalities, we need our and or. So this is an and problem. So to get rid of the absolute value, I bound x between 2 and negative 2. I can equal 2. So the graph of x is equal to 2. It's a solid boundary line. So at 2 and negative 2, I'm sorry for the non-straight graph. X is between those numbers. Okay, so if x is between negative 2 and 2, then it's going to be the region exactly between the vertical lines. Okay, 5 is greater than the absolute value of y minus 1. I'm going to change that so the y is written first. So absolute value of y minus 1 is less than 5. This is another and problem. So to get rid of the absolute value, I bound the region between negative 5 and 5. Adding 1, negative 4 is less than y, which is less than 6. Okay, these are solid boundary lines. So at y is equal to dashed boundary lines. At y is equal to negative 4. And then at y is equal to positive 6. Again, I need all my y values between those two numbers. So I shade between my two horizontal lines. Okay, so where's my solution? My solution is the overlap of the shaded regions. So my solution set is x is between negative 2 and 2, and at the same time y is between negative 4 and positive 6. Okay, that'll do it for this one.